Alright students, so in our last session we discussed about the vapor pressures of liquid and liquid solution. We discussed about Rowlett law. We discussed how Rowlett law becomes a special case of Henry's law. We learnt about the mole fraction of liquids in the solution phase, in the gaseous phase. What is P naught, what is P. So today we will be doing ideal solutions, non-ideal solutions and some colligative properties. So let's start with ideal solutions. Now what are ideal solutions? Alright. So we are talking about liquid in liquid. If we are talking about ideal solutions, here we are considering liquid in liquid. That is two liquids together. Alright. So the solutions which obey Rowlett's law over the entire range of concentration. This is important. Concentration. It's not about temperature and pressure all the time. It's mainly about concentration. So the Rowlett law can be applicable over the entire range of concentrations of for a solution, that solution can be called as ideal solution. Alright, so what do you mean by applying Rowlett's law? That the equation, the statement which we had written, equation P is equal to P naught into X or P1 is equal to P naught 1 into X1, that should become valid throughout the concentrations. For all the concentration, we should be able to get P is equal to P naught into X. How to find out the validation? By calculating P every time and P naught into X every time and making LHS equal to RHS at all the concentrations. If you are getting both the sides equal, this means that law is valid for that particular solution. So that becomes ideal solution. Alright, that's the first criteria. The second criteria, change in enthalpy of mixing should be zero. Change in enthalpy of mixing should be zero. What does that mean? Okay, alright, I'll explain you. First, change in enthalpy means change in energy of mixing when you're preparing the solution. So what happened? If I want to call a particular solution as ideal solution, what should I do? When I add two solvents together, when I add solvents to each other, like if I mix two solvents, then there should not be any heat liberated or gained. So there should not be any change in the heat, change in the temperature, change in the energy. If that happens, then that solution is called as ideal solution. What is ideal solution? When solution is being prepared, that time no energy should be evolved or gained. Such solutions are called as ideal solution. That's the second criteria. What is the third criteria? When I mix, there should not be volume difference. What does that mean? If you remember in a previous session, somewhere I put this statement that volume is not an additive property. What do you mean by that? Volume is not an additive property. If I take 80 ml of water and 20 ml of ethanol, I add. I expect solution to be 100 ml, but I don't get. I get little less than that. Why? Because I have explained that. Why? Because ethyl alcohol get trapped in the empty spaces of water molecule. So the volume will be always little less than 100. So there is a difference. What I added 80 plus 20 and what I'm getting is not perfectly 100. It is less than that. So the difference between two is not zero. It is more than zero. Alright. So ideal solutions will be wherein you add two solvents of some volume and the expected and the observed volume is same. So there is no difference in the volumes of the reactants and the product. Then volume change of mixing will be zero. If that is happening, then that particular solution can be said to be ideal solution. Alright. So 1, 2, 3 criteria. The next criteria. Suppose I am adding A and B. So I have A solvent, solvent B. They are together making AB solvent. So what happens when I have solvent A? So there will be A molecules together. So one A molecule will have some interaction with other A molecule. That's why it is liquid. When something is liquid, it means there are some interaction between two molecules. So yes, there is interaction we can see here. Similarly, when I take solvent B, again there is an interaction between B and B. Alright. So these interactions are there. When I mix, I get new interactions. When A is mixed with B, I get new interactions. A forms new interaction with B. B forms new interaction with A. Now, when we compare the strengths of these interactions, this found to be equal. The strength of interaction between A molecules, strength of interaction between B molecules, and strength of interaction between A and B is equal. If it is equal, then this particular solution is said to be ideal solution. So what are the examples? When you mix N-hexane and N-heptane, N-hexane, N-heptane. N, everyone knows, normal straight chain compound. So when you mix hexane and heptane together, they nearly act as ideal solutions. See, no solution can be ideal at 100%, but almost they are acting as ideal solution. Benzene and toluene. Everybody knows the structure of toluene, benzene with CH3. So such two solvents when mixed, they behave as ideal solution. Next up is bromoethane and chloroethane. So bromoethane and chloroethane together act as an ideal solution. Alright. So I'll quickly summarize what is ideal solution. There are 4 criteria for a solution to be called as ideal solution. First, solution should obey Raoult's law over the entire range of concentrations. When two solvents are mixed, their enthalpy change of mixing should be 0. Difference in the volume of mixing should be 0. The solvent having individual interaction, those interactions should be equal to the interactions which are present in the solution. If these 4 criteria are fulfilled, then the solution is said to be ideal solution. Examples are hexane heptane together, benzene toluene together, bromoethane and chloroethane. So this is all about ideal solution. Next, let's move towards non-ideal solution. Alright, so this is non-ideal solutions. So in non-ideal solution, we have 2 types. One is positive deviation and one is negative deviation. Now what do you mean by positive deviation and negative deviation? If you remember that graph which we had studied for vapor pressure of 2 volatile liquids are mixed together, I have that graph in the next slide, so don't worry, I'll be explaining that. So positive deviation is one category in which the interactions which are formed between new solution like solvent A and solvent B, when the solution is prepared of A and B, whichever the new interaction is formed, that is weaker than the interaction between solvent A and solvent B molecule. If that is happening, then the vapor pressure increases and graph will be above the line of the ideal solutions. Alright, what is this? I'll tell you. See, when I have only solvent A, so because this interaction is comparatively strong, this A molecule is not allowing other A to go out and form vapors. They are not allowing each other to go and form vapors. Similarly happening with B. But when they are together, what is happening? New interactions are made between A and B, which is weaker. Because this is weaker, A is allowing B to go, escape out and form vapors. Similarly, B is allowing A to go and form vapors. So more amount of vapors are formed. So pressure will be more. So because of this new interaction, the solution will have more vapor pressure than the individual solvents. So in the graph, we see positive deviation for this kind of solution. For example, ethanol and acetone. So together, individually, if I talk about ethanol and acetone, yes, they are volatile solvents, but together individually their vapor pressure is less. When I mix, why ethanol's vapor pressure is less? Because one ethanol molecule is bonded to another ethanol molecule by hydrogen bonds, which is a type of interaction which is quite strong. But when I add acetone to ethanol, what happens? This acetone goes and break that hydrogen bond which exists between 2 ethanol molecules. Okay, so this H bond will be broken. So now this ethanol, which is have broken hydrogen bond with the other ethanol molecule, forms a new bond with acetone, which is not a hydrogen bond and it is quite weak. So now this acetone is allowing ethanol to go and form vapors. Ethanol is allowing acetone to go and form vapors. So more vapors are formed, more pressure will be created. So vapor pressure will increase. So this is about positive deviation. Now what is negative deviation? Here the individual solvent have interactions which are quite weaker. So when solvent A is kept and B is kept, they are allowing each other to go and form vapors because the interactions between 2 A molecules, 2 B molecule is weak. So basically they are going and forming vapor pressure is more. But when you mix these, these two solvents, new interaction is formed AB. This interaction is quite stronger than this two. So now A is tightly holding B and B is tightly holding A, and they are not allowed to go out and form vapors. They are in the liquid state only. That's why no more vapors are not formed. So pressure will be also less. So vapor pressure will decrease and you will get graph below the standard line. For example, if I have phenol and aniline. So first I have one beaker in which I have kept phenol and another beaker in which I have kept aniline. Alright. So in phenol, what happens? One phenol molecule is attached with another phenol molecule by some weak interactions. So both of them can go and form vapor. So vapor pressure is quite greater. Same case of aniline. But when I mix phenol and aniline, they form hydrogen bond. How? The OH ka H of phenol and lone pair which is present on nitrogen, they together form a strong interaction, and these interaction, because of this interaction, the vapor pressure decreases, because now this phenol is not allowing aniline to go and form vapors and aniline is not allowing phenol to go and form vapors. That's why the less vapors are formed and vapor pressure will be less. Another example is chloroform and acetone. So chloroform and acetone together, when they are mixed, they are forming hydrogen bond, not allowing each other to go out and form bond. That's why to form vapors. That's why the vapors are less, pressure is less, therefore vapor pressure will be also less. I'll show you what is positive and negative deviation in this graph. I have not labeled this. You just have to see. See, these green lines are the standard graph which we have studied. So in case of positive deviation, what is happening? In case of positive deviation, I see the graph red line, dotted red line is the positive deviation. The graph is going above. Because the vapor pressure is more, the graph will be always above the line in case of positive deviation. In case of negative deviation, because the vapor pressure is less, the line will be always below the standard line. The standard line are for ideal solution and this is for non-ideal solution, positive and negative deviation. I hope we are clear with this positive and very simple. In case of positive, how to remember? Positive deviation means graph vapors are more. That's why the graph is above the line. So vapor pressure is more because vapors are more. If vapors are more means new interactions are weaker. And negative deviation means vapor pressure is less. Pressure less means vapor less. Vapor less means interactions are stronger. They are not allowing each other to go and form vapors. So this is how we deal with non-ideal solution. Next up we have azeotrophs. Next up we have azeotrophs. Alright. So now, what are azeotrophs? Let's learn. This is also a type of solution. Same composition in liquid and vapor phase. If you remember, in the previous session we did how to determine what are the terms we use for knowing the composition. X1 and X2 we use for liquid and Y1 and Y2 we use for vapor phase. Alright. So when X1, that is the composition in liquid phase, is equal to Y1, that is the composition in vapor phase, are equal for a particular solvent. Similarly, X2 will be equal to Y2. Then we say those solutions are azeotrophs. Okay. And they are also not able to, we can't separate those azeotrophs by fractional distillation. We use this method when there is a difference in the boiling point is less. So it is not easy to separate them by only using distillation. So we use method fractional distillation. But azeotrophs cannot be separated by even fractional distillation. Once they are formed, they are formed. For example, minimum boiling azeotrophs and maximum boiling azeotrophs. Minimum boiling azeotrophs, what does that mean? The solution will boil at lower temperature. If something is boiling at lower temperature, it means it is highly volatile. If it is highly volatile, it will make more vapors. The vapor pressure will be more and the graph will have large positive deviation for Raoult's law. Are you getting what I'm saying? Minimum boiling azeotrophs. Minimum boiling means something is boiling at lower temperature. If something boils at lower temperature, it means we are talking about volatile solution. Volatile solution produce more amount of vapor. More amount of vapor will produce more vapor pressure and large positive deviation will be seen. Example is ethanol plus water. This logic you need to understand. Maximum boiling azeotrops, boiling point is high. Solution is non-volatile. Non-volatile means less vapors. Less vapor pressure, it means large negative deviation from Raoult's law. This RL is nothing but Raoult's law. Example is 60% HNO3 and 32% H2O. When mixed, they form maximum boiling azeotrops. Whichever nitric acid you see in your lab, that's nothing but 68% HNO3. Nobody gets 100% HNO3. So whatever you see in the lab, it always contains water. Then too, it is highly concentrated and highly corrosive in nature. Alright. So azeotrops, same composition in liquid and vapor phase. They are not, we can't separate them by fractional distillation. There are two types: minimum boiling azeotrops, maximum boiling azeotrops. Minimum boiling azeotrop, large positive deviation will be seen. Maximum boiling azeotrops, large negative deviation will be seen from Raoult's law. Example is ethanol plus water, and for maximum boiling 68% HNO3 and 32% H2O when mixed together. Alright. Now we are moving to the core part of the, what we say, chapter, very important part of the chapter, that is colligative properties. Alright. So this colligative properties are very, very important. There are 4 colligative properties we will be learning, and those colligative means to bind together. And the very, very important thing which you have to learn from this, which you should remember, that these property depends on number of solute particles irrespective of their nature. So how much solute you are putting inside any liquid, depending on that, the colligative properties will vary. Alright. Which solute you have added doesn't matter. What you have added, that matters. So these property depends only on the solute particle. These are called as the colligative particles. Alright. So we will be doing the first colligative property, relative lowering in the vapor pressure. Okay. Before that, we will be doing a simple demonstration to understand that what happens when the vapor pressure of solution of solid decreases. Okay. So before that, I'll be showing you one demo. From that demo, you will understand what exactly happens. Alright. So let's see that demo first, and then I'll continue my explanation. Alright students, so in front of you now you can see there's one container in which I have taken water. Okay, this is a very simple demonstration, but then too I want to make clear idea of vapor pressure of everything. Now in this container, till this there is a water, liquid water, and you see empty space over the water till the lid, right? So in this empty area, we know what are there? There are vapors, not only of water, of other gases also. Now these gases are putting pressure, exerting pressure on this surface of the water, right? So this is called as a vapor pressure. Now that vapor pressure is maximum because this is closed. If I open this container, then now the vapors are escaped out. Because the vapors are escaped out, there is a less vapor pressure. But whatever vapor pressure is there, because of the water molecules, because water molecules are always also on the surface. On the surface, there are only water molecules which are escaping out to the maximum and forming some vapors. Now what I do, this is a pure solvent. So whatever pressure is exerted by the vapors of water on the surface will be denoted as P0. Now what I do, I add a solute to it. See, I have taken little salt, I am adding to this. Now I am stirring a little to make this solute dissolve in it. Alright. Now, I guess most of the salt has dissolved in it. So now no more, if there are little, just ignore it. So now salt is dissolved inside. It is homogeneous solution. I cannot find out where are the salt particles. So this salt particles will be at the surface also. So now the surface of water also has some
salt particles also. When I had not added the salt, only water molecules were there. So more number of water molecules were available for escaping out and forming vapors. Now this surface has some salt particles also, some salt molecules also, which will not go out and form vapors. Only water will go. But the amount of water molecules to go and form vapors will be less. So now whatever vapor pressure of this solution, it will be denoted as P, and that will be less. So what you want to learn from this, what I want to convey, that P naught, pressure of water, pure water, is more than the pressure of water when you add something in it. If I add salt, sugar, whatever, what happens, the number of molecules available for the escaping out, forming vapors, are less at the surface. So that's why pressure of solution, vapor pressure of solution, is less than vapor pressure of pure solvent. So P is always less than P naught. That's it.
Alright, you have understood. Now see, this is one thing I have to explain you. Vapor pressure of solutions of solid and liquid. Now what is this? We had taken water. So water is my one component, and C2 was solid. So if C2 is your solid, that solid will never contribute in the vapor pressure of the solution. So vapor pressure of the solution, for that the only contributor is your solvent, that is water. That's why when you want to write about the vapor pressure of solution, you will write only in terms of 1. Not for the solute, only for the solvent. So this is the only statement come. If you remember, for we used to write P2 is equal to X2 into P2. Why? Because our second component was also liquid, in case of liquid and liquid. But when we are talking about solids and liquid, we will write only one statement, that's for liquid, not for solids, because solid doesn't contribute to the vapor pressure. That's why look at the graph. The graph has only one line. If you remember, the previous graph has 2 lines because there were 2 components. Here only one line. There were total pressure P1, P2. Here only one. Vapor pressure increases as mole fraction of solvent increases, because only contributor to the vapor pressure is solvent. I hope you're clear with this, why this graph is simple and why that graph has 2 lines, because there were 3 lines actually, one for total pressure, one for P1, that is pressure of component 1, and P2 for pressure of component 2. But here only one component, that's why no total pressure, only one total pressure is nothing but the pressure given by the solvent. So I hope we are clear with this. Now we are going to learn this. Our first colligative property is relative lowering in vapor pressure. Okay, relative lowering in vapor pressure. Let's try to understand what is this. So I am talking about a solution which I showed you demo. Same solution. So water and salt. So solvent and solid. So I have written about the vapor pressure of solvent. So P1, that will be the vapor pressure of solution when I have added salt to it. So I'm talking this phase when water has salt in it. What is this? Mole fraction of water, mole fraction of solvent. Now 1 is always only about the solvent. What is P01? It is the pressure of solvent when it is pure, right? So we are clear with this. What is P1? Pressure of solution, vapor pressure of solution. Solution means solute plus solvent. What is this? Vapor pressure of pure solvent when you haven't added anything in it. There is nothing in it, only solvent. What is X1? Mole fraction of solvent in the solution when you have added. So 1 and this term, 1 and 2, these 2 terms are talking when you have solution. Only this not denotes about the pure solvent. So this is for solution and this is for solvent. Alright. So this is clear to you because we have written this equation many a times. Now what is this? This is the difference in the pressure. What is P01? P01 is the pressure of pure solvent.
and we are subtracting the pressure of solution. I explained in the demo why the pressure of solution is less than pressure of solvent. What is solvent? Remember this, make this thing clear in your mind. This is P01 is pressure of pure water, vapor pressure of pure water. What is P1? When salt is added to water. So this is less than this. Why? I explained in the demonstration. Alright. Now I know what is P1. I have value for P1 here. So I put it here, x1 into P0 into 1. Then I take this common P01. So I get 1 minus x1. So everyone knows 1 minus x1 is nothing but x2. Because we are studying binary solution. So we are considering binary solution. So 1 minus x1 is nothing but x2. So this is the formula we are getting for lowering. Lowering means how much, by what degree it has lowered. So this is delta P1 is equal to P01 into x2. But you know what they have asked? They are asking relative. What do you mean by relative? So by what was the standard and what has happened? So I take out the difference. So that difference has to be compared with the standard. For example, when we calculate your marks, you give 100 marks paper. So normally what is expected? 100 marks. But what you get 70. So what do you write? 70 upon 100 into 100. That's your percentage. So what you got, divide by what you should get. This is called as a relative. Similarly, what I have got, what is the difference? Delta P1 divided by the standard. What is standard? The vapor pressure of pure solvent, P01. So we are dividing P01 on both the sides, left hand side also, right hand side also. So here it get cancelled. So this term is called as relative lowering in vapor pressure, and which is equal to x2. So what is x2? Mole fraction of solute particle, amount of solute particle. So this definitely depends only on the number of solute particles or amount of solute particle. That's why this is a colligative property. It depends only on the amount of solute present in the solution. So I hope, are you clear with this? You're clear with this? How this came from here? What I did, I took out P01 common. I get 1 minus x1. I know 1 minus x1 is equal to x2 for binary solution. If it is not a binary solution, I have many components, then I cannot write x2. But in this unit, we are doing only binary solution. So 1 minus x1 is equal to x2. Then what is happening here? I divided on both the side by P01. Why? Because I want to calculate relative lowering vapor pressure. Relative lowering in vapor pressure, not lowering in vapor pressure. So to calculate relative, I divided both side by P01. Here it get cancelled. I get x2. That shows this property depends only on the mass of the solute particle, amount of the solute particle present in the solution. That's why this is a colligative property. Now we have done further process in this. Let's see that. Alright, so you can see this. So delta P1 divided by P01 is equal to P01 minus P1. This we know. Difference in the pressure divided by P01 is equal to x2. This is nothing but formula of this here is equal to x2. We know x2 is equal to N2 upon N1 plus N2. So for very dilute solution, very dilute solution, we can simply neglect this N2. So after neglecting, I get N2 upon N1. So what is N2? Number of moles. Everybody knows. So W2 upon M2. So N1 will be W1 upon M1. That goes up and it becomes M1 upon W1. So this is the final formula, can be used to calculate numerical. I'll tell you, when you are solving problems of NCERT, when you are doing this problem in your unit test, in your board exam, you can simply use this formula by neglecting N2. Okay. But when you are solving your engineering or board, medical entrance exam or any other entrance exam, please do not ignore this N2. Okay, this is only given in NCERT. I'm not sure about the answers outside the NCERT like for other exams, but I'm sure about this. your board exams. There you can simply use this formula by neglecting N2, because this is given in our NCERT. So I hope this is also clear to you. See, in this chapter only you should be clear with these terms. What are these terms? When the numerical come, you should be able to find out what is P0, P1. So you keep reading, keep repeating to yourself, what is this, what is this, what is it. Once you are clear with all the terms and you are able to find out, then it is very easy. We will be doing numericals to make you understand that what is P0, what is P01. So we are moving to the next colligative property, and that property is elevation in the boiling point. Alright. So we are doing now elevation in the boiling point. Okay. So this is second, what we say, colligative property. So see, one thing you have to remember, whatever is written, these properties are comparison between pure solvent and solution. So what was the boiling point of pure solvent? And when I add some solute to it, what happens to its boiling point? So the whatever difference is happening is because of amount of solute you have added. So by that I can know how much solute is there. So for this elevation of boiling points, lowering in vapor pressure, depression in freezing point, you remember this is about solute, pure solute and solution. Okay. So there is one graph given. Before that, let's understand this terminology. Again, if there is a knot, it means it is a boiling point of pure solvent. This is the boiling point of solution, and this is delta T base difference. What does that mean? Suppose I'm talking about salted water. So what is the boiling point of pure water? What is the boiling point after adding salt to it, and difference between their boiling points? So this is we are going to learn. So I have this graph is given in the NCERT. So let's try to understand by this. So this is before that we have to understand what is boiling point. All right. So boiling point is nothing but when you start boiling a liquid. All right. So it will boil at certain temperature. Before that, it starts preparing or making vapors. Okay, so slowly that vapor starts increasing. Those vapors create vapor pressure on the solution, on that solvent, on that liquid. That vapor pressure and atmospheric pressure when the vapor pressure of liquid matches with the vapor pressure of, atmospheric pressure, that at that temperature, that particular liquid starts boiling. I know till 11th or till 10th, you know definition, the point, the temperature at which liquid starts boiling is called as a boiling point. Correct. But what does exactly happen at that temperature? At that temperature, vapor pressure of that liquid, you should understand, you should visualize what is vapor pressure. Some vapors are formed on the surface of the liquid. That vapors are creating pressure on the surface of the liquid. That pressure and the atmospheric pressure outside that container, outside the test tube, fusion tube, whatever pressure is there, that atmospheric pressure. So these two pressures when equal, that time liquid starts boiling. Now let's come back here. On this graph on y-axis we have taken vapor pressure. Here we have atmospheric pressure. So from here vapor pressure increases and matches here to the atmospheric pressure. Here we have taken temperature. Now these are the lines for vapor pressure of solvent and solution. So in the previous colligative property we studied lowering in the vapor pressure. It means solution has lower vapor pressure than solvent. That's why solution's curve is below solvent. See, solution's curve is below solvent. Solvent's curve is up. So what happens at this temperature? At this point, vapor pressure of solvent matches to the atmospheric pressure at this point. So what is the temperature corresponding to this point? This. So this is the boiling point of your pure solvent. See, when the solution curve is matching to the atmospheric pressure here. So what is the corresponding temperature? TB, which is more than T naught B. That means the boiling point of solution is more than the boiling point of solvent, and the difference is delta TB. I know this graph is not making things that clear. You just go through this term. I have very simplified graph which will explain you what is elevation in boiling point. All right. So let's go to that graph. Okay. So see, simplified graph. This is my graph to explain everybody. So I've drawn one line. This line is telling me about the vapor pressure. Vapor pressure is increasing from bottom to the top. So this highest point which I've noted with red color, this atmospheric pressure, our expectation. Here we want to go. Now here is my vapor pressure of my pure solvent, only water. It is here. And I have added some salt to the same water, so its vapor pressure will be less. Because we have studied vapor pressure of solution is less than the vapor pressure of solvent. So when I'm boiling only liquid, that is pure solvent, that pure solvent vapor pressure is here. So that pure solvent has to cover one journey from P0 to atmospheric pressure. Means this much. This much difference solvent has to cover, right? But when I'm talking about solution has to start from here. So solution has to cover more difference. To cover more difference, more temperature is required. That's why its boiling point will be always greater than the boiling point of the solvent, because solvent has to cover lesser distance and solution has to cover more distance. Very simple. If you are starting from if you are starting from nearby, if you stay nearby to your school and if you are coming to school, you need less time. The one who is coming from station needs more time. So this time we will correspond to temperature. That's why solvent requires less temperature. Less temperature, low boiling point. Comparatively, solution needs more temperature to cover more difference. That's why solution's boiling point will be more. So delta TB difference will be TB minus T0B. What is TB? So boiling point of the solution. What is T0B? Boiling point of pure solvent. Alright. So now what is the mathematical expression for this? Let's see that. So mathematical expression is delta TB directly proportional to M. Delta TB I just explained. What is M? Molality. Molality is nothing but amount of solute present in it. Alright. So Kb into M. So Kb is boiling point elevation constant. This they give, or this sometimes they ask us to calculate. It varies from solvent to solvent. It is not same for all solvent. It is not universal, but it is a constant for all the temperature and pressure. Alright. So what is M? Molality. We know the formula of molality. We have already done W2 upon M2 into W1. If this is in gram, we have to multiply this by 1000. So just go through this once. Alright. So here today we finish ideal solution, non-ideal solution, azeotropes. We were talking about the vapor pressure of solutions of solid and liquid. How solid doesn't contribute to the vapor pressure of solution because solid is incompressible, doesn't produce any vapors. Second thing we see, why when we add solute to the solvent, how does it reduce the vapor pressure? That we discussed in the demo. Then we started with the colligative property. First we did relative lowering in the vapor pressure and then we did elevation in the boiling point. More to go, that we will finish in the next session. Before that, I'll be doing some numericals with you so that you will understand what are these properties, how do we use it in numericals, because from this chapter numericals mainly come for board exam. By the time I again suggest, please keep reading your NCERT, please go through this terminology. This will make you master. Once you're clear with all the terms, all the symbols, it will be easier for you to understand the concept, to use the concepts. Alright, so I just hope you all will be doing these things again and again to become master in that. So I'm ending my session here. Thank you and stay safe.